Alrighty, so now we're going to talk about this twist distribution that we can use to develop this, or to create this Prandtl bell-shaped lift distribution. So in 2019, let me get my color fixed. In 2019, Phillips and Hunsaker, let's see, 2019, there we go. They published a paper looking at this Prandtl bell-shaped lift distribution and looking at how we would develop this twist distribution to be able to produce that bell-shaped lift distribution. So I didn't want to spend too much time writing out these equations. These are the equations that we've looked at before. The only difference is that we've drawn out the B1 coefficient over here, which is, again, that's just A1 over 1, so that's 1. And then over here we have all our other B sub n's, where n is greater than or equal to 2. So this is how we define our section lift distribution. This is how we relate our B sub n to our A sub n coefficients. This is how we relate our span-wise coordinate to our theta value. And then this is the solution to that equation once again. That's our lift distribution, and this is our minimum induced drag, given this series sum of B coefficients, B sub n coefficients. So what Phillips and Hunsaker found was that this twist distribution right here and this twist amount satisfied those equations. And so you can see it can get pretty hairy, and that's a big reason why I didn't want to write it out for you guys. But you'll notice all these B sub n's right here, all these series sums of these B sub n's, and what they looked at was, well, what if we take Prandtl's bell-shaped lift distribution? So once again, that's where B sub n is equal to -1 over 3. What if we took that lift distribution, or excuse me, that lift distribution and applied it to these guys? And so if you assume that B sub n is 0 for n not equal to 3, and B sub n is -3, you end up with the following. It simplifies it down quite a bit. So we have omega of theta, and I'll add little curlies on my omega, is going to be 4b over CL alpha tilde times 1 minus B3 all over C root minus sine of theta plus B3 sine of 3 theta, all of that divided by C of theta, close bracket. And then we're going to add on the end here minus 3b3, all of that, plus 1 plus, times 1 plus sine of 3 theta divided by sine of theta. So that's our whole numerator divided by 4b 1 minus b3 divided by CL alpha tilde C root minus 12b3. Okay, so that's our twist distribution, and our twist amount is the following. It's a little bit easier. CL over pi RA times 4b times 1 minus b3 all over CL alpha tilde C root all minus 12b3. Okay. So this is, well, a couple things I wanted to talk about here. So you can see if we were to remove the B3s from this equation, in other words, if we were to say B3 is equal to 0, what we would find, and I'll give myself a little bit more space here, we would find that we could go back to that elliptic lift distribution. So that's just going to be 1 minus sine of theta all over c of theta divided by c root. And then our omega becomes 4b CL divided by pi RA CL alpha tilde c root. Okay. Now, looking over here, we can see what that. Let's get a better color. Blue could get confusing. Let's do green. So we can see here our bell-shaped lift distribution and our elliptic lift distribution. And so you can see that when we're trying to minimize this wing bending moment, we're going to bring that lift inboard to take care of the fuselage weight. And you can see down here what that does to all our kappa coefficients. So over here we've got omega. So this is our washout distribution, and you can see it for a function of taper ratios and as well as for the elliptic planform. Now, something to note about that is that since this is not a planform, the elliptic planform is not optimized to produce minimum induced drag. In this case, for this Prandtl bell-shaped lift distribution, you would have some twist on that wing. Now, once again, the bell-shaped lift distribution is not the distribution that minimizes induced drag, right? And we go back to that definition. It's the one that minimizes induced drag for fixed gross lift and fixed wing, moment of inertia of gross lift. And over here we can see our washout amount coefficient that goes in our CL equation. So let's write that out real quick. So we've got CL is equal to CL alpha times alpha minus alpha L0 minus epsilon omega omega. So we can see, similar to before, it's actually a little bit more drawn out here for the bell-shaped lift distribution, but there's for the most of the time, adding washout will decrease our lift. There's very few scenarios where it'll increase our lift. Okay, and so here's our lift washout coefficient, and you can see how that changes as a function of aspect ratio and taper ratio. And so if we go back once again to these equations, CDI is going to be CL squared times 1 plus kappa D minus kappa DL, CL, CL alpha, omega. I'm writing a little bit big, so let's see if I can, make it a little bit smaller. Okay, plus kappa D omega times CL alpha omega squared. All of that divided by pi RA. So now taking a look back over here, we're going to increase induced drag, or excuse me, we're going to decrease induced drag in this range, and now over here we're going to increase our induced drag as a function of taper ratio and aspect ratio. And the last thing is, over here we've got, and I guess one more thing to note over here, the elliptic planform kappa DL is 0. And our epsilon omega is 1/4 for the elliptic planform. Okay, so here's our kappa D omega for tapered wings, and here's our kappa D omega for elliptic wings. So once again, you can kind of see this trend that in order to minimize induced drag, we'd kind of want to have a lower kappa D omega. And you can see the same thing over here. We'd actually want to decrease our aspect ratio to minimize this kappa D omega coefficient. Now, once again, these are all different variables. These are just trends that I'm drawing on here. So I'll go back up here and say and reiterate, this is our twist distribution and our twist amount for minimizing induced drag for the Prandtl bell-shaped lift distribution.